Zaczynamy, nie mogło być inaczej, od sztucznej inteligencji, tego jak może się przydać w systemach gospodarowania wodami opadowymi. Między innymi o tym opowie nasz pierwszy gość specjalizujący się w cyfryzacji sektora wodnego. Kierownik i uczestnik wielu projektów ukierunkowanych na tworzenie rozwiązań opartych na AI dla zarządzania zasobami wodnymi i infrastrukturą, dr Ricardo Taormina z Politechniki w Delft.
Wow, nice slides. Hi everybody, nice to see that many of you made it here today despite the fun of yesterday. I'm going to talk about what I believe to be the most interesting trends in artificial intelligence connected to stormwater in particular, but this is also applicable to the water sector more in general, and also to other forms of critical infrastructure. And this would be foundational AI models and AI agents. So let's start from foundational AI models. So you can think of them as general AI brains, which are trained on a lot of data, using a lot of computational power, not to solve any specific task in particular. And this is known as pre-training, so basically we would like these models to learn very widely usable and reusable patterns from the data, again, without solving any specific tasks. Once you have such a model, then you can refine it, you can fine-tune it, using a much smaller data set usually to solve, indeed, specific application of interest. And probably the most famous case of this foundational model versus fine-tuned model is ChatGPT. So ChatGPT is a refined model, a fine-tuned model, from a foundational model which is known as GPT. GPT was trained for months on a huge amount of data, on very large cloud infrastructure, to solve no specific task, just to learn from the entire World Wide Web and beyond. And then ChatGPT was refined from this model to work as a helpful assistant. If we move to our field, where physics, chemistry, biology is really, really important, then the concept of foundational AI models changes, I would say, drastically, meaning that here we're mainly interested in replacing our simulators, and I will tell you why in the next slide. But if we had to have such a foundational AI model that can replace simulators, this means that this model should be able to really, truly understand the sewer network processes, whether physical, chemical, biological, and also, for instance, flooding, how water interacts with building, with the infrastructure and whatnot. And even in this case, ideally, we will be able to access a huge amount of data coming from different cities, different settings, different storm events. And if we manage to train such a foundational model, then we can, again, use fine-tuning with much less data to solve specific case studies, whether it's for real-time control or predicting CSOs, or as well maybe tailoring a specific tailoring this foundational model to your specific city, district, and whatnot. Why would we want to do this? We love our simulators. Many of you guys here, I think, share my thought. Well, even though simulators are getting faster and faster, and it's incredible, the improvement that we are having, for instance, with processing on GPUs, AI will always be faster than that. But I think the most interesting thing, especially if you look at the future, where data is going to be more available, whether from telemetry or remote sensing, the ability of AI to digest directly this type of data is always superior, and largely so, than that of simulators that always require some form of fine-tuning, calibration, which can be very tedious, right? And also this flexibility of AI can grant them more robustness where we are lacking very important information. And at the same time, if you look at the future where AI is going to be used in all utilities for whatever reason, then it's also kind of like credible that this system will be 5 years from now easier to deploy and to maintain than traditional simulators. But we do have strong challenges. We always hear in our field, okay, the water sector is data rich but information poor. If you want to truly build a foundational AI model, we are simply data poor. We will never have the entire, the huge amount of data that they use to train GPT. Different utilities have always different standards. This data is critically, safety critical, so it's difficult to share. We know all this, right? So it's going to be very difficult to find enough data. And also, of course, this AI simulator, there's still going to be most likely black boxes. We're going to lack the level of transparency and trust that we have in our simulators, which are based on our best understanding of the physics behind our systems. So in the past 5 years with my AI lab at TU Delft, I tried to see whether there is a solution, whether we can overcome these challenges. And we came up with a strategy, if you will, made of 3 main steps that we believe can lead to the development of successful foundational AI model for the water sector that can truly replace our simulators. So first of all, you don't just build any general, however big type of AI model. You build AI models that can embed the physics in it. So these are known as physics-guided AI models. And also this model should be extremely data efficient. And this means that they truly have to understand the type of data structures that we're dealing with when working, for instance, with stormwater system. So networks, meshes. If we do this, then we have this physics-guided and data-efficient model that we can actually pre-train on simulations. So I say before that we want to replace the simulators, but we can still use high-fidelity simulators to create synthetic data to overcome the lack of real-world data that we have because we are dealing with stormwater systems. And if you do the second step also nicely, then we can truly do a final level of refinement using whatever real-world data we manage to gather and put them in a standardized format that we can then leverage using training a single model that uses all this data to truly make sense of what's going on. And data can be telemetry, can be from remote sensing, theoretically can be anything, even tweets, even citizen science. AI has theoretically this capability. But it is, of course, difficult, and that's why in these 5 years, we managed to arrive only to step 2. But I want to show you that even in this case, we do get something interesting and useful that we can already use. And I work in the Netherlands, so for instance, flooding is a big problem there, as you may know. We developed an AI model that kind of replaced simulators for flooding. We are now extending to pluvial floods. I'm going to show you here a case of dike bridge floods. So, in the Netherlands, we have a lot of dikes, and therefore this is a big issue. So I'm going to show you how our model behaves in a real-world, realistic application. So this is an area near the city of Nijmegen, the border with Germany. It's a pretty complicated case study. We have 280 square kilometers of area, and we have a lot of infrastructure there, roads, canals, lakes, and so on. Now, what you see here is the performance of our model against the performance of the simulator, which is Delft 3D from Deltares. It's a major consulting company in the Netherlands. And you should be able to see that on the second column, you see the performance, the prediction, the spatiotemporal evolution of a dike bridge flood as modeled by Delft 3D. And on the third column, you see what the AI is doing. So I hope you can see that they're in very strong agreement, also the evolution, and the difference is small. And we use only a very limited amount of simulations to train our AI model. So this is good because we have pretty strong accuracy, but we have huge speed ups. So our model is 10,000 times faster than the original simulator. So when you have this type of speed up, then you can do a lot of interesting things. You can think about real-time response. You can think about multi-scenario analysis or probabilistic flood mapping, which is what you see here. Now, I've been talking now about replacing the simulators, but I think everybody here is more familiar with another type of aim that AI in general has in the years to come, right? Which is replacing us, humans, whether engineers, managers, anything, anyone. And this is what AI agents are meant to do, okay? So everything starts, let's say, before 2022 with these foundational AI models that has been trained on the entire World Wide Web, it's difficult to say, to learn nothing specifically, but they display the very strong capability to really understand, model human language, regardless of the language, and also coding. Then, fast forward, let's say, to November 2022, ChatGPT was introduced, this fine-tuned model that acts as an assistant that truly changed the world. A little bit later, I think 2024, we start seeing these LLMs, these large language models, which are now multimodal, meaning that they are able to work, also reason, in quotes, about images, about videos, about sounds. And then, since 2025, all the attention has switched to these LLM agents, these AI agents. These are basically an ensemble of an LLM, and around it, let's say, an orchestration layer, a software that interface these systems with APIs, databases, web search, computer terminals, and many other things. And also these LLM agents are refined to perform what is known as reasoning, which in the end is basically planning. So they take a big task, then they divide it in smaller tasks. They try to do each of these individually in a sequence until they solve something quite complicated. And everybody's talking about this, but is this really going to happen? 5 years from now, there'll be 50% of the people here and the rest all computers, or not. For sure, the huge hype that we have and all this funding going to these AI labs is because they are promising us that they're going to deliver artificial general intelligence, AGI, something that can truly replace humans in many, many tasks. Now, progress is steady because, every new version of ChatGPT is usually better than the one before. The same goes, for instance, for Claude and so on. But before, we could resort to scaling up until probably 1 year, 1.5 years ago. You just use more data, more compute, bigger models, and then you have a jump in the potential performance of these models. This is not happening anymore. And also, still today, all of these big AI labs, they're burning money. They're really burning money. They are not profitable, even the most successful ones, okay? So we're using this model, subsidized because of all this hype and because there is this belief that 5 years from now they're going to be really good. And business value is not always there. But for sure, there are some applications in which this model are really changing what's happening. And then coding is one of them, basic software engineering. But this does not mean at all that, it's going to be true across all other type of applications, for instance, those that we might be more interested in. So with my lab, we are trying to see the potential of these AI agents for, let's say, the water sector. So we are basically trying to study what can we get out from them. And the first thing that we did was, checking how these multimodal agents could actually, if they could help sewer inspectors in their job. Can they look at CCTV images from sewers and then, tell us if there is a defect in there and maybe give us a report and tell us, what they're seeing? And if this works, then maybe we can use it as a starting point for the type of robots that Professor Ashley was introducing yesterday that may roam our sewers in the years to come. So we have a data set with some, images of pipes in good conditions, other with defects. You can see here the type of defects which are quite common in our sewers. And then we truly ask many different types of LLM, okay, tell us what you're seeing, all right? And on a scale of 0 to 1, where even humans don't get 1, so usually we are at 85, 95%, so 0.9, more or less. That's what the human level should be. If you look at GPT-5, it's not that good. It's below 50%. It's good at recognizing easy defects, the more complex one, not at all. And even if you look at the more recent version of it, 5.1, 5.2, it is not improving at all. So that's the plateau that I was describing. And if you actually use a much smaller and older model also for OpenAI, you do actually have better results. So again, these capabilities, even though they're improving, it doesn't mean that this translates to an improvement in our field, okay? And if you build a model that just does that, much smaller, and we did this, we just published a paper on this, you get much better results on much more complicated tasks. So our model there works on 18 different class of defects and still does better than the one that's just looking at 5 class of defects. And this model hallucinates all the time. And it's fun to see how they can get things wrong. So, in this case, there's a production error and they think it's roots. I don't have time to go into the details. I made an application to showcase this. So if you want, you can scan it. You can go on Hugging Face and you can see all the beautiful hallucinations of these models on sewer defect detection. Okay, I got 5 minutes left, and I want to talk about potentially what is the most interesting type of agents that we could build. And I call them spatiotemporal reasoning agents. Why? Because, better than I do, being mostly in the practical side of things, that, we are dealing with widely distributed systems. Everything is interconnected, right? So this interconnection is key to our systems, okay? I cannot take that image and then just throwing it to ChatGPT and ask ChatGPT to make sense of it. You will find nothing at all, right? Very complex data structure. And we are dealing with systems that change in time. They're dynamic, so the temporal component is also essential. And this is true at the large scale, the entire water systems, a city, a district, but this is also true, if you look at water plants, treatment plants, right? We have interconnected components, spatially interconnected, and of course dynamics that change constantly. So we're also looking into this, and we started from, I would say, the slightly simpler case study of a water plant. So this is something that we did with Waternet, which is the water utility, water authority of Amsterdam. So they were really interested in seeing, okay, can these agents make sense of the spatiotemporal nature of our processes, of our systems? So they gave us access to a pilot plant. They gave us the PNID, the process in instrumentation diagram of the plant, which is a simple plant with only 3 major heat exchangers. And still, though, we're talking about hundreds of interconnected components. We're talking about, I think, 40 sensors for temperature, turbidity, flow, and whatnot. So we wanted to see whether we could interface such a thing, such a plant, with an agent, right, to create what it could be maybe an interactive digital twin if you keep working on it. And this is what we did. And again, it's not that we can take the image of the PNID, whatever format, and just throw it to ChatGPT or whatever model and expect something out of it. No. We had to create from this graph, from this graph, we have to create a knowledge graph that then the agent could navigate. And within it, also the sensors that were deployed in the system. And once you do this, you really see that actually the agent can navigate the plant, can understand what is connected to what, can understand also, the scope of the entire plant without any specific information about it. And what we did was also trying and test this model, this agent, to solve more complicated tasks, which have been done by engineers in the water utility. So the most complicated things that we asked the model to do was to compute the degradation of the heat coefficient as the plant was used, because biofilm was forming in the pipes, in the heat exchanger and whatnot. So this is not like a very trivial task. So it takes probably half or a full working day to a medium expert engineer. Now, I don't think I have the time to show you all the interaction, but basically, after we create this orchestration layer, after we truly link the AI with the underlying knowledge graph of the plant and the sensors on it, then you can see that actually, once you ask this type of questions, with a good prompt, the model starts really navigating the system, understanding for each heat exchanger, the type of heat exchanger, what pipes goes in, what pipes goes out, the sensors that need to be retrieved for the right time frame in order to compute the final results. And it was not perfect. It's not like a zero-shot things. I had to correct this a few times. But then, in 5 minutes, I was able to get this graph on the left, which is essentially the same graph that the engineers at Waternet got in much more time, okay? So what do I want to say with this? Is that I think AI is here to stay. You know, I work in it, so, you know, I hope so. I'm very optimistic about it, but, you know, with a grain of salt, of course, okay? So this could be possible because I put my knowledge into it. You know, I did the prompt, I made all the connections and whatnot. And even when we look at foundational AI models, there's a huge potential there, but we still need to, you know, make them work, gather the data, go out in the field. As someone said yesterday, that cannot be replaced. And I believe that's the case in general. But, you know, embrace them, but, you know, always be aware of your domain knowledge and the fact that you are difficult to substitute. Okay? Thank you so much.